Bo. So that email that HR sent out, so like that was in relation to those one-on-one meetings, right? That they claim was just getting to know you.
Oh, yeah, dude, I saw that. Just both started long.
At least I didn't set mine up early.
Fine, was mine someone up though?
All right, another exciting day in Trig. And today we're actually going to get into the biggest part of Trig, which is right triangle trig. So basically, just so we're aware, all right, so we're lecturing this today, and this actually won't take all class. So we'll have a little bit of time to take a look at those activities and discuss that a little bit. And we're finishing the material for actually the part 1 quiz, all right, on Tuesday. All right, so then what I typically do is then I lecture to the next part just a little bit. It won't be on the quiz, all right? And then we have the quiz, so that way there's usually like a week between us finishing the material and us actually having the quiz. But the big thing about all this is in Trig, we have actually a lot of quizzes just so we keep, because we need to keep fresh on so much different stuff. All right, so I have it designed where we have more quiz, and then each day is not quite so crippling. Oh my God, like half my grade is on 2 day. Okay. All right. So as for today, all right, right triangle trig. And in case everyone does not know, which everyone of course should, the Pythagorean theorem, the greatest theorem in geometry. And this then comes down to how trig is broken down as well. But instead of calling things a squared plus b squared plus c squared, we typically identify an angle. We have an angle of interest when we identify our triangles. And from there, we identify, all right, we still have the hypotenuse. We call that guy H, all right, which is, of course, the side opposite the right angle. Then we have, all right, what we call the O side or opposite side. And then the A side, the adjacent side. So we still have the same exact formula, O squared plus A squared equals H squared, instead of A squared plus B squared equals C squared. But in trig, we always have an angle of interest. And so you see we have our angle theta, because if I move theta to up here, then this side becomes A and this would be O. The hypotenuse doesn't change. But that's because when we actually create our trigonometric equations and our trigonometric functions, it's based on which one is opposite the angle, which one is adjacent to the angle. All right, so some other notes. Again, things that we need to know: what an acute angle is any angle between 0 and 90, obtuse angle, any angle 90 to 180. Which then brings us to the big acronym for our trigonometric functions. All right, SOHCAHTOA. And you may remember this, right? You may have at least seen this. SOHCAHTOA, and this breaks down what each of the three fundamental trigonometric functions are. So, which is sine opposite over hypotenuse. Cosine is adjacent over hypotenuse. And TOA, tangent, is opposite over adjacent. Now, I do want to make one other note when we're talking about trigonometric functions. A trigonometric function, all right, sine, cosine, tangent, and their reciprocals. Notice it's read as tangent of theta. So typically we drop the parentheses, but that's tangent of theta. That's similar to when we write square root, right, x plus 1. That theta can't be pulled out. It is of tangent of the angle. And so way often, all right, do your best to not write tan. All right, tangent of what? All right, it's just like writing, oh, square root. Square root of what? All right, it's about what is this in relation to that makes this function important. And so that's a big fact, all right, that we just forget so often. All right, so these are do nots. And these are do's. And it happens to all of us, and I know, and when we really start getting into doing a lot of like messing around with all these functions, all right, it's very tempting to do this part, all right? Do your best to remember it's tangent of an angle, tangent of something. Okay, so SOHCAHTOA helps you identify your basic trigonometric functions. Now, the good news is these guys down here, these are all the reciprocal functions. So notice that cosecant is just the opposite of sine. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. Basically, once you find SOHCAHTOA, once you find these three, all you have to do is flip them to find the other trigonometric functions. And so cosecant, secant, and cotangent, you're probably much less familiar with than sine, cosine, and tangent. And the reason is simple. In application, we use sine, cosine, and tangent much more than their reciprocal functions. However, all right, these do have their place. They're just used significantly less. All right. All right, so let's look at an example. Examples are always helpful. So I want to find all the trigonometric identities of a triangle with hypotenuse 5 centimeters. And notice the side adjacent to the acute angle theta is 3 centimeters. And, all right, I'm not told any additional information. But the good news is that with Pythagorean theorem, I can find the missing side. And that means O, the opposite side, equals 4. And this is by far the most famous triangle, all right, of all time. You've probably seen this one, the 3, 4, 5 right triangle. The 3, 4, 5 right triangle is just such a common right triangle. In fact, all right, a lot of contractors hold, all right, when they're identifying, doing walls and things like that, they have a 3, 4, 5 made triangle. That's usually like 3 feet, 4 feet. So they like put it up to make sure. But all right, the 3, 4, 5 is one that everyone remembers. And the nice thing about the 3, 4, 5 is it expands. It's the same as if I multiply everything by 2. A 3, 4, 5 is the simple version of a 6, 8, 10, right? And a 9, 12, 15, etc. All right. So, all right, the 3, 4, 5 is the most famous triangle. So from there, then I can find all my trigonometric functions. And the easiest way to do it is just write out SOHCAHTOA. So, ka. Toa. And literally plugging in our values. Now, be aware that I can also then reverse engineer this to find the actual angle theta. That's not what we're doing at the moment. This is the sine of theta equals 4/5. And that's a much better number than if I do the inverse function of sine, I could actually find what that angle is. All right. And we will come a time when we're doing that, not what we're doing at the moment. Then all the reciprocals. Cosecant of theta, secant of theta, and cosecant of theta. Once you have the functions, the reciprocals are exactly what we would want them to be. Sine, the reciprocal of sine is cosecant, which means that's 4/5, and 1's 5/4, etc. 3/5, 5/3. And that's all we're looking for there. Easy peasy stuff. So, along what I was just saying, the reciprocal identities, right? We almost never find secant, cosecant, and cotangent directly because it doesn't have the nice acronym SOHCAHTOA. You identify SOHCAHTOA, and once you have that, and actually SOHCA is all you ever need, right? If you know that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, you can find the remaining 4 trig functions every time. Because, all right, there's also what's known as quotient identities. Tangent is just sine over cosine. And there's so many of all these functions are just related to each other, right? And this turns out that we end up with so many nice ways to find all the remaining ones given just one trigonometric function. And again, if tangent is sine over cosine, the reciprocal function of tangent is cotangent, which is then cosine over sine. And so a lot of these, all right, as we practice through these, we're going to see that once you know one, you know everything else. All right, so along those lines, by being told what I just said, sine is √7/2 and cosine is 2√7/3, I can find the remaining trigonometric functions using all that reciprocal identity stuff. So let's start with the easy ones. Cosecant of theta, which is 1/sine. And secant of theta is 1/cosine. So that means I end up with the opposite of this, which is 2/√7. And the opposite of that, which is 3/2√7. Now, this brings up a big point, all right? And it's something that my math lab is going to make sure you're doing, all right? I'm not as particular about it, but you should know, all right, how to do this. Specifically, 2/√7. Is it okay to leave an answer in this form? Guys remember our algebra at all? Or no, we don't.
You can't have a square root in the denominator.
Right, you're not supposed to have a square root in the denominator. Does anyone remember what that's called? How we fix that? What that term is called? Rationalizing. And specifically, we call it rationalizing the denominator. So we need to rationalize the denominator. You may remember this when you had imaginary values, same thing, right? Imaginary numbers, they can't be in the denominator. Square roots shouldn't be in the denominator. You should never have a decimal within a fraction, you know, basic, like kind of arithmetic, algebraic like concepts. In order to get rid of that, the easy thing to do is multiply by that same square root. I'm going to multiply it by root 7 over root 7 because root 7 over root 7 is just 1. So I'm not changing the problem at all. This then becomes 2 root 7. And then root 7 times root 7 is. What is it? I thought I heard someone mumble it.
1.
Nope.
7.
7, right? Because root 7 times root 7 is root 7 squared, and then square root go away, so it's actually just 7. And so that's the very, very common thing. Root 7 over root 7 is 1, right? Root 7 times root 7 is just 7. So along those same lines, I need to rationalize this one as well, and I multiply by the same thing. This becomes 3 root 7 all over 2 times 7, which becomes 3 root 7 over 14. Now, conceptually, right, it is just the reciprocal. 3 over 2 root 7 is exactly the correct solution for secant of theta. But I do this because, one, in the activity solution, I almost always rationalize. Now, on a test, don't fret, leave it unrationalized. I'm absolutely fine. I'm looking for the concept that you understand it's the reciprocal. But my math lab, it will not let you not rationalize, okay? So make sure you know how to do it. Okay, so we use the 2 reciprocal identities. Now let's use the quotient identity. Tangent of theta is sine theta over cosine theta. And we have both of those, which means I have root 7 over 2 divided by 2 root 7 over 3. And this brings up another like little algebra test. Can I leave a fraction within a fraction? No, what do I need to do? What's that process called where you fix this? Does anyone remember? And really, it's like not the process, but the little phrase that you to fix this. Leave it. Change it, flip it. Leave it, change it, flip it. All right. So you leave it. You leave the top one. Root 7 over 2. Flip division to multiplication, or change division to multiplication, and flip the denominator. Leave it, change it, flip it. All right, also known as multiplying by the reciprocal, but everyone always remembers leave it, change it, flip it, right? Because that's how you deal with a fraction within a fraction. And then simplify this down, let's see, 3/4. Beautiful. All right, the root 7's cancel, and then 2 times 2 is all flat. And last, but definitely not least, cotangent of theta. Now I could find this by doing cosine over sine, or better yet, cotangent of theta is just 1 over tangent theta. Which means now I have 1 over 3/4, aka 4/3. And that's always identifying the SOHCAHTOA and then flip them to get the remaining cosecant, secant, cotangent. And so none of this math is hard, all right? We just notice how fast our cheat sheet is building already, all right? On your cheat sheet, you just have tons and tons, all right, of these little identities. Now, eventually, you'll start to like memorize, especially the simple ones, reciprocal and stuff like that. But in the beginning, your cheat sheet, that thing should be packed with these types of formulas. Okay. The fundamental identity, right? And all these are called fundamental identities, but the fundamental identity in trigonometry is sine squared theta plus cosine squared theta equals 1. All right. A fundamental identity means that is the most important identity in that entire topic. All right. There's a fundamental identity. There's fundamental identity of algebra. There's a fundamental identity of arithmetic. All right. Every field of mathematics has a fundamental identity, which means this formula right here, that one goes at the top of your cheat sheet with stars, highlights, and asterisks. To see why this is the fundamental identity, let's do a very simple proof. I want to start with the Pythagorean theorem. O squared plus a squared equals h squared. All right, so the Pythagorean theorem, which FY is the fundamental theorem of geometry. All right, because they are, and the whole concept is they are the most used theorems that exists in that field. All right, so I take this and I'm going to divide this whole thing. Divide both sides by h squared. And with all algebra, as long as what I do to one side I do to the other, I can do whatever I want. So this becomes O squared divided by h squared plus a squared divided by h squared equals h squared divided by h squared. And then to make this a little prettier, I'm going to rewrite this. And then h squared divided by h squared is
1.
Is 1. All right, so now that I've rewritten this, notice what we see here. Opposite over hypotenuse quantity squared plus adjacent over hypotenuse quantity squared equals 1. What is opposite over the hypotenuse? Sine. So look at what this becomes. Sine theta squared plus adjacent over hypotenuse cosine. And what we have is our fundamental identity. Now notice that I have it written as quantity squared. That is what this little notation means, where you write sine squared of theta. That actually means sine of theta quantity squared. It's all about like kind of shorthand notation. You can write them either way. And in the beginning, all right, a lot of times people like to write it like this because when you start having these powers, they get confused as to what's happening, which is absolutely fine. Either way, whether you write it in as sine theta quantity squared or sine squared theta, those are the same. All right, there are two other fundamental identities, but they are not nearly as fundamental as the first one. And really, these other two fundamental identities are creations based on the first one. So if I take our fundamental identity and I'm going to divide this, divide both sides by cosine squared theta. So what we have, right, and this now I could write this as, let's write it out actually. Cosine squared divided by cosine squared is 1. So pulling the powers out so we can see actually the exact trigonometric functions. Sine divided by cosine. Tangent. One divided by cosine. I know we literally just learned them, but which one's 1 divided by cosine?
Secant.
Yeah, secant. Which means, look, that's what the second fundamental identity says. Tangent squared theta plus 1 equals secant theta squared. And then similarly, I could prove the last one, cotangent squared plus 1 equals cosecant theta squared, by doing the same thing, but instead of dividing by cosine squared, I would divide by
Cosecant squared.
simpler than that. I divided by cosine. Instead of cosine, how about sine? Always start with the easy stuff. Sine and cosine are what we use the most fundamentally. So instead of dividing by cosine, I would just divide everything by sine squared, and I could end up with the other one. And I get the exact same proof. I go through the exact same proof, but divide by sine squared. Yeah, you're overthinking it. I was like, easy, easy. Always start easy. Okay. So along those lines, all right, now we're going to talk about how to use our calculator either later or next class, all right? But using reciprocal identities, we can actually solve things that look really, really complicated very, very quickly. Tangent of pi over 8. So it's important to understand, instead of saying tangent of theta, this is, all right, the angle. Pi over 8 is an angle, all right? It's some, I mean, and we're most familiar with degrees, it's something in the neighborhood of like 20 degrees. Tangent of 20 degrees results in a value. But using my quotient and reciprocal identities, I can simplify this down. So I have tangent of pi over 8. Then I have minus sine of pi over 8 divided by cosine of pi over 8. Well, what is sine divided by cosine?
Tangent 1.
Tangent, right? It's not the same. Same things divided by themselves are 1, right? Sine divided by cosine is our quotient identity. So this becomes tangent pi over 8. Tangent of pi over 8 minus tangent of pi over 8. Charlie?
It's 0.
Is 0. Right? Something minus itself is 0. So even though this looked crazy complicated, it just results in 0. Using those little quotient identities, quotient and reciprocal identities, and this carries throughout the rest of the course. I mean, we use these identities all the time. Similarly, all right, I have sine squared of pi over 12. So not much I can do with that. That's sine squared of something. And I have secant. And whenever possible, the rule of thumb is get everything into sines and cosines. All right. Especially when you have secants, cosecants, cotan, I mean, all that stuff. It's just like, ugh. Sines and cosines are the fundamental piece that everything is built upon. So always try and get it to that. Now this one, right, the first one, I actually turned sines and cosines into tangent because it was easy, but I also could have just turned tangent into sine and cosine. So I would have had sine over cosine minus sine over cosine, and it still would have ended up the same thing. All right, so secant is 1 over, are we getting better?
Cosine.
Cosine. All right, so I have 1 over 1 over And once again, what are we gonna do? What's the phrase? Leave it, change it, flip it. Right? This actually means 1 over 1 over 1 over cosine. Flip, flip, flip. This becomes and then look at this. Sine squared of an angle plus cosine squared of an angle is one. The fundamental identity. All right. This is always something that's why I said the top of your cheat sheet. This fundamental identity, being able to recognize this, helps everything. So it's nice. Trig, Trig is so much better than algebra because it's just so elegant. I was like, it's just so beautiful, of how we can do things. Trig has lots of applications too, but today we're just looking at the beauty of it. All right. So given just one trigonometric function, it is possible to solve for the remaining 5. Right? And we're going to see that basically by the end, given just one piece of info, not even a full trigonometric function, I can find all 6. All right. And that's really the beauty of all this. All right. So tangent of theta. So let's always do the easy one first. Cotangent of theta, its reciprocal function 2 is 2. Exactly. Now, the other way to do this, and we could mess around and we can use the fundamental identities to find the remaining, right? But the other thing, don't forget that this is a triangle. And there's really 2 ways to do this. I could solve this with the identities, all right, and with the reciprocal functions. But a lot of times, do the easy thing and make your triangle. Tangent is what over what? Soka to what? So opposite over adjacent. If I know that I have opposite over adjacent, can I solve for the hypotenuse? Using what fundamental theorem? Pythagorean theorem, all right? Once you have your triangle filled in, then I can go back to SOHCAHTOA and let's find sine of theta, cosine of theta, and then we can find their reciprocals. All right, so sine is which one again? What's the phrase? Let's say it. So. Whole thing. SOHCAHTOA. All right. I was like, I know it seems ridiculous. Say that to yourself over and over. That's one that you want memorized. You shouldn't have that on your cheat sheet because we use that all the time. SOHCAHTOA. And I'm sure if you YouTube it, there is a dance or something. I guarantee someone has done it. All right. So, all right. So, opposite over hypotenuse. Adjacent over hypotenuse. All right. And now, as a note, I could rationalize, but again, as long as you got practice rationalizing, as soon as you understand how to do it, I don't do rationalizing anymore because it's just spends time. All right. Then the reciprocals, cosecant of theta and secant of theta. All right. Another big theorem we use is the complementary angle theorem, which most of the time when we use this, call this CAT. All right, complementary angle theorem, CAT. This comes down to the concept of, all right, a complementary angle by definition, okay, are two angles that sum to 90 degrees. All right, angle plus an angle, right, sums to 90 degrees. If I know I have a right triangle, one angle is 60 degrees, the other angle is then 30 degrees. This then relates to our trigonometric functions because they're co-functions of each other. And the nice thing is when they came up with the naming scheme, they just put the word co in front of them. The co-function of sine is cosine. The co-function of tangent is cotangent. The co-function of secant is cosecant. Oh, look at that. All right. The naming scheme was not totally random. All right. It relates to how these functions relate to each other. What that means, all right, is that any angle 90 degrees off of it is its cofunction every single time. All right. Pi over 2, all right, we talked about our radians to degrees. The biggest one you need to know is that the angle pi over 2 equals 90 degrees. Pi over 2 radians is 90 degrees. And I guess while we're at it, so this is rads. How many revolutions for 90 degrees? A quarter, right? Since just while we were at it, these are our 4 ways of measuring angles: revolutions, degrees, and radians. So a quarter of a revolution, which is equivalent to 90 degrees, which is equivalent to pi over 2 radians. All right. So that's what this angle says. It says that 90 degrees off of each function is its cofunction. Sine of theta, cosine 90 degrees off of theta. Tangent 90 degrees off of cotangent. Now this opens up, all right, that we're then able to make even more equivalencies, all right, and identify angles and then use our reciprocal and our fundamental identities to really solve problems very, very quickly. So along those lines, sine of 30 degrees is equal to cosine of 60 degrees. Tangent of pi over 12 is equal to cotangent 5 pi over 12. Because, right, when we add these up, pi over 12 plus 5 pi over 12 is how many pi over 12s? Pi over 12 plus 5 pi over 12 is 6 pi over 12s. 6 pi over 12s reduces down to pi over 2, which makes it 90 degrees. And that's what all these say. 30 degrees plus 60 degrees is 90. 80 plus 10. And that's why these are equivalent. The function and angle, the cofunction, and the remaining pi over 2 or 90 degrees. What that means is that now look at all these different angles we have. Using the complementary angle theorems, our reciprocal and our fundamental, we can get this all the same. Now, our first goal when doing problems and doing any problem is get your angles the same, all right? And the quickest thing to check is 28 plus 62. What number is that? 90. Oh, look at that. That's super good news. And then it doesn't really matter, all right? Do you prefer 28 or 62? 62. Prefer 62. All right, so, all right, the cofunction, that means I need to turn this guy into 62. The cofunction of secant is cosecant, right? It's so easy with the name, cosecant. And we just said 90 degrees off of 28 degrees is 62 degrees. And oh, look at that. Cosecant of 62 degrees minus cosecant of 62 degrees is, get your calculator out, 0. See how beautiful that is all the time? And this is the biggest thing with trig, way often. If you are guessing blindly in the dark, your guesses should be 0, 1, or infinity? Those are the guesses. All right, similarly, all right, 35 and 55 degrees, and so I have sines and cosines in here. All right, 35 plus 55 is 90. As soon as you see that, you should always be thinking cat. All right, complementary angle there. All right, so once again, I need to think cat, and do we prefer 35 or 55?
35.
35? Is that what you said, Brandon? Okay, 35. All right, so that means get your angles the same. That one stays the same. Plus, I'm going to fix that one. Plus something sine of 35 degrees. Okay, sine of 55 degrees. The cofunction of sine is cosine. So that becomes cosine 55. Sorry, sine 55 becomes cosine 35. And the cofunction of cosine is
Sine.
sine, right? So you don't add it, it's not cosine, you just drop the co. So that becomes sine of 35 degrees as well. Now notice what I have. Cosine of 35 degrees times cosine of 35 degrees. Could I write that another way?
Cosine 35 degrees squared.
Squared. Similarly, sine times sine is sine squared. So I have cosine squared 35 degrees plus sine squared 35 degrees, which is 1. 1, because this is the fundamental, right? I put the "the" on there because, all right, all three of those are technically fundamental identities, but this is the fundamental because the other two are really based off of this. All right, so, all right, the fundamental identity. Oh, look at that. And look at it. 0 and 1. See? Guessing in the dark. Good. All right. All right. So once again, so given cosecant of theta equals 4, I can find all kinds of different stuff using basically everything that we talked about today. All right. So sine. So if I know cosecant of theta equals 4, how does cosecant relate to sine? So now we got to start digging into our bag of tricks. How are cosecant and sine related? They're reciprocals. Okay, good news. So sine of theta equals 1 over cosecant of theta. And if I know that cosecant of theta was 4, oh, look, I have sine. Okay, so now we're looking for cotangent squared of theta. Does cotangent relate to cosecant and in any way? And this one, a big trick, cotangent squared, which means where should I be looking? If I have a trigonometric function squared, what should be one of the things I'm thinking about, or the main thing? What of all the stuff we talked about has squareds today? Pythagorean theorem, but that doesn't have any trigonometric functions in it. But that's close. That is super close. We use
Cat.
nope, cat doesn't have squareds. And so notice how big our bank got already. I was like, we talked about a lot of stuff. What had squareds? Fundamental identities. All right. All the fundamental identities, notice, are trigonometric functions squared. All right. So whenever you see a squared, all right, and again, you have the fundamental and then 2 other fundamental identities. All right. So notice which one has, I already forgot, was it look cosecant or cotangent? Whichever one. Oh, look, here's a fundamental identity that involves both cosecant and cotangent. So and this is the least used fundamental identity. All right. The fundamental identity cotangent squared plus 1 equals cosecant squared. All right. So if I have cotangent squared and I have cosecant, that means that I can mess around with this. So if I put, okay, if I bring the 1 to the other side, cotangent squared theta actually is cosecant squared theta minus 1. So adjusting the fundamental identity by just bringing the 1 to the other side, I can actually rewrite it for what the question was asking for. And I was given cosecant theta, which means I had 4 squared minus 1, which means cotangent theta squared is just 15. Do we see how we're kind of messing around with the identities and the algebra here? This all looks kind of tricky magic, right? But I was like, this is very, very common. This is what we, in Trig, we have all these identities and all these relationships, and we just kind of mess around with them until we get what we're looking for. All right, secant of pi over 2 minus theta. Okay, so secant of pi over 2 minus theta. We actually saw this notation already. In what theorem? Cat. All right. When you see this, cat should flash to your mind every single time. Because it's saying 90 degrees off of something. What is the co-function of secant?
Cosecant.
Cosecant, right? So the co-function of secant is cosecant. And remember, 90 degrees off of theta is just theta. And look at that. We were given cosecant of theta is 4, which means secant of pi over 2 minus theta is exactly cosecant of theta, which is also 4. And that's the beauty of what cat does.
No, that was.
Oh, that was just super easy, right? For something that looks complicated. And be aware that when people see this pi over 2 minus theta, they try and make this much harder than it is. Cat is, keep going back to the definition of what the complementary angle theorem actually says, because it just says 90 degrees off of it. And to actually prove that, right, the two angles, pi minus 2 theta plus theta, right? When I add these two together, what do I get? Pi over 2, aka 90 degrees, right? So even though these don't look like these add to 90 degrees, they do. I was like, it's super easy to see when we have 35 and 55 and 62 and 28, right? When we have numbers that we can attach to, it's very, very simple. But don't forget, all right, that this is the generalized definition. Okay, and last but definitely not least, secant squared theta. Once again, when you have squareds, what possibly should come to mind? A fundamental identity. In this case, the fundamental identity is tangent squared theta plus 1 equals secant squared theta. And actually, the only way to get to this, all right, given what we've already accomplished, all right, so if I'm looking for secant squared, which means I actually need tangent squared of what we've already found, what is the closest thing to tangent that we have?
Cotangent.
Cotangent. We actually found cotangent, which means I can use that to find tangent. Tangent is the reciprocal of cotangent. Oh, which actually brings up something interesting. So, sidetrack real quick. Our reciprocal identities. Cotangent and tangent are reciprocals, right? Of all the relationships, tangent and cotangent are also complementary angles. So, right, cap, tangent, cotangent. They're the only one that is both the reciprocal, all right, and the co-function of itself. They're just fun relationships. So lots of things are related. That one has an interesting relationship. Okay, so I had cotangent, which was 15. Cotangent squared, which makes that 1/15. So now I have tangent squared. So in order to find secant squared theta using my identity, if I have tangent, that means that's 1/15 plus 1 makes that 15/15, makes that 16/15. Using my fundamental identity to find secant squared. And so every time you can get one piece of info and then many things are asked, and every time I was just looking back and I was saying, oh, given what I have, the only way to get to secant is I have to get to tangent, which means I have to get to use cotangent to get to that. All right. Lots of interesting relationships that we're gonna be investigating. All right. So we've got 25 minutes. Let's actually talk about the activities. All right. So this first activity, all right. So this covers 5.1, 5.2, what we did Tuesday and what we did today. All right. So you notice that number 1, that's basically what we did in 5.1. All right. And then number 2 is things that we were talking about today. All right. So we have a little time, but I'm actually pretty lax about what you do in here. I always recommend that you at least attempt the graded problems, but I understand we all have lives, we all got stuff to do. So like if you have to go, you have to go, no problem. Like I said, I don't take roll. I mean, actually I pretty much have everyone's name already. So I was like Brianna, Macy, Charlene, Catherine, Brandon, right? Did I mess anyone's up? Brianna? Okay, all right, just make sure. All right, so I was like, I don't take roll beyond these first couple weeks just for bookkeeping, but otherwise I was like, I recommend you take a look at it and you have questions, please do so. But like I said, we're not gonna have a lot of time. I mean, 25 minutes is about as much as we're ever really gonna have, all right? And I set aside, like I said, on the 6th, that whole day is basically an activity day. I'm not doing any lecture. And that day is really just a question day where ideally you've looked through most of the activity, and if you have questions, please let me know. But again, every time. All right. So take a look at the activity. Otherwise, you have yourself a wonderful weekend. All right. And I was like, it's been a great first week of Trig. Yeah. It's like, how are we doing in our 1450, Brianna, Catherine? And I was like, I mean, yeah, you guys have only had one day, right? I was like, so the first day was probably good. All right. Abel, Jada, Shannon, are we okay online? Any questions, concerns? By your silence, I'm going to assume that things are just going fantastic. All right, you guys have yourselves a good weekend as well.